All right, we're going to go ahead and move on to our next section, which is to find inverse functions. And this is where we're actually going to algebraically solve for inverses. So we're going to use that same idea that instead of x's going to y's, y's go to x's, and how they kind of get swapped. So before we get into solving for functions, inverse functions algebraically, I want to show you what it looks like and the correlation between a function and its inverse when they're both graphed. Okay, so let's go ahead and look at this first one, and it says we're given the plot of f of x. Okay, so this is our f of x line, and what we want to do is we want to find the plot of the inverse. Okay, so what I'm going to do is I'm just going to pick out some important key points here. Okay, I noticed that this point right here, it almost looks like it's at 0. I don't think it's quite on the line, but I'm going to look at that point. I'm going to look at this point because it's at 1, 1, and that's an easy point to see. And then I'll see if I can find another point, maybe at 3, that kind of looks like a good point. Now notice this is going to keep going on further, right? And I could even kind of approximate that as like 4.5, maybe is at 8. I don't know. So I'm just going to pick several points so that I have a good description of my graph, kind of like we did with the parent functions and the transformations. So I'm going to list here that f of x has the ordered pairs. Well, at -1, I'm almost at 0. I think this represents an exponential function, which we'll see some of those later. So instead of putting 0, I'm just going to say 0-ish. Okay, because I can't really tell if that hits the line or if it's just getting really close to 0. Okay, then our next point is at 1, 1. So 1, 1. And then we have 3, 4. And then we have, let's see, this last one is maybe like at 4.5, 8. Maybe 4.5, 8. Okay, it doesn't have to be perfect because we're just sketching a plot. Okay, so we're going to use that same idea that if our original function sends an x to a y, then if we want to graph our inverse function, then all we have to do is swap our ordered pairs. Okay, swap. Okay, so when we swap them, now we have y's, like 0-ish, going to -1. We have 1 going to 1. We have 4 going to 3. And we have 8 going to 4.5. Okay, so that's how we can plot the inverse, is just by reversing our ordered pairs. Notice I'm not changing signs. I'm just literally swapping x's with y's, right? So now that I have this, I'm going to go ahead and graph it to see what it looks like. So at 0-ish, right, so somewhere right here at 0, we're down at -1. At 1, I'm at 1 again. At 4, I'm up at 3. 1, 2, 3. And at 8, I'm up at 4.5-ish. Okay, so when I graph this, notice should have the same shape. And what's neat about inverse functions or graphing inverse functions is that when you graph inverse functions, they're actually a reflection of one another. So remember how we talked in the transformation section about reflecting around like the y-axis, right? And we talked about reflecting around the x-axis. So when we talk about inverses, it's actually a reflection of itself about the y equals x line, because we're taking our y's and x's and swapping them, which creates a mirror image on that diagonal line. So you can see this side looks exactly like this side, right? And over here looks exactly like over here. So it's like this diagonal line creates our mirror. So let's look at one for y'all to try. I want you to identify the points just like I did on this one, swap them to get the inverse, and then double check to see if it looks like a mirror image across that identity line. So go ahead and pause the video for just a moment and work that out, and then play it to check yourself. All right, so let's see how you did. The points that I identified, again, are this one that's really close to 0, or it might actually be on 0, I can't tell. So I went ahead and wrote it as -4, 0-ish. Okay, then our next point is -2, 2. And then our last point is 0, 7. Now, if you identified some other points within here, that's totally fine, but you just need to make sure you get enough that your shape accurately represents the function that you were given, okay? So now that I have those f of x points, all we have to do is swap them, change our x's and our y's to get a graph for our f of x function. So when I plot that f of x function, indeed, you can see that this is a reflection about the y equals x line, right? Because what looks like over here, if I were to flip this over across this line, it is indeed that reflection. Okay, so this is our f of x, this is our f inverse of x. Okay. All right, awesome. So let's look at another way of looking at inverses, and that is to determine whether a function has an inverse based on its domain. So remember, in order for a function to have an inverse, it must be one-to-one. So a one-to-one function passes the horizontal line test, okay? So this one says the graph of y equals f of x is shown below. Although it is not one-to-one, we can restrict the domain. So we can restrict what x values we're specifically looking at to make it one-to-one so that it will have an inverse, okay? On which of the following domains given in interval notation will the restriction of f of x be one-to-one? Select all correct answers. Okay, so what we're doing is we're looking at, in this range of x values, will we have a piece of this graph that passes the horizontal line test? Okay, so I'm just going to put a note here. Passes the horizontal line test. Okay, in order for it to be one-to-one, it must pass a horizontal line test. So let's look at this first option, -8 to -3. So we're looking at this function from -8 to -3. So here's -8 and here's -3. So between my finger and the pen, would just this piece right here pass the horizontal line test? And it would, right? If I draw any horizontal line on that piece, it's only going to cross one time. So that one works. Yes, that is a solution. Okay, let's look at the next one. The next one is from -6 to 2. So let's go over here to -6 and then over here to 2. So every piece of this graph between my two fingers, would that pass the horizontal line test? And we can see easily that it would not, right? Because I could draw a horizontal line right here and it's going to hit 2 times, one on each side of this peak, right? So that one does not work. Okay, let's look at our next one, -5 to 0. So if I start here at -5 and I go over to 0, again, that peak is still included. So that's going to cause a horizontal line to hit more than one time. So that is also not an option. What about -5 to -1? So -5 now to just -1. Well, that's a little bit better, but still not, because it still has the peak, which means if I draw a line right here, it's going to hit 2 times, right? So still not okay. Let's look at -3 to 2. Let me get a pencil. That's a little bit easier than my hand. So at -3, we're here, over to 2, which is here. So between my pencil and my pen, you can see that this is just a straight line. It doesn't include that peak, right? So any horizontal line I draw over this piece of the graph is only going to hit one time, which means that it would be one-to-one. So I can use that -3 to 2. And then our last one that they're giving us as an option is from -6 over to -1. And you can see here that from -6 to -1, that's going to include that peak. And so if I draw a horizontal line anywhere in here, right, it's going to hit it twice. So that means it's not going to be one-to-one. So we only have 2 intervals here that were given to us that would create a one-to-one function. All right. All right. So I want you all to try it. Same idea. Okay. Go through and determine which of the following intervals will create a one-to-one function that will have an inverse. Okay. All right, so hopefully you gave it some thought, and the only 2 correct intervals that we should get that would cause this parabola to be 1 to 1 is the interval from -2 to 3, because from -2 out to 3, this will pass the horizontal line test, right? And then also from -7 over to -2, this curve from here to here will also pass the horizontal line test. Okay, every other option that was given included this dip, and if this dip is included, then when you draw a line across, it's going to hit more than one time, right? If it hits more than one time, it's not 1 to 1. It doesn't have an inverse. Okay. All right, so let's go ahead now. Now that we understand, we've talked about finding inverse function values off of a graph, off of a table of values. We now understand limiting our domain. So all we have left to talk about is now how to solve for these inverses algebraically. So to find an inverse algebraically, we're going to use what's called the swap and solve method, okay? And here's what it looks like. First of all, we're going to take it out of function notation because f of x gets a little bit stinky to work with if you leave it in function notation. So we're just going to replace our f of x with y, and then we're going to swap all of our x's and our y's, just like we do in our table of values, right? We just swapped our ordered pairs. So in our equation, anywhere we see an x, we're going to write a y. Anywhere we see a y, we're going to write an x. And then we solve the equation for y, okay? Now that will give us our inverse function once it's resolved for y. So then once we have it solved for y, now we just put it back in function notation by replacing y with f inverse of x. Okay, so let's go ahead and look at a couple. Now notice on all of these that you are asked to find the inverse, if you see something like this, this just means they're restricting the domain so that it will have an inverse, okay? Because here, this is a parabola, right? When you see an x squared, that's going to make a parabola, and parabolas don't normally have inverses, right? Because they don't pass the horizontal line test. So what this is saying is that it is just going to be taking only that positive side of the parabola so that it passes the horizontal line test so that we can solve for the inverse, okay? So don't pay too much attention to that other than it means it's a domain restriction that will allow this function to have an inverse, okay? All right, so we're going to use our steps here. We're going to replace our function with y. So I'm just going to write this as y is equal to 5x squared plus 4. And then we're going to swap. So I want to swap all of my x's with all of my y's. So anywhere I see a y, I'm going to write an x. Anywhere I see an x, I'm going to write a y. Okay, so now it is in inverse function form, but it needs to be solved for y, just like all of our equations that we deal with, right? So I'm going to go ahead and move my 4 to the other side. I can do that by subtracting. So x minus 4 equals 5y squared. Okay, and then I divide off my y to get y by itself. Okay. I'm going to come up here because I kind of ran out of room. So I have y squared is equal to x minus 4 over 5. And then I need to get y by itself because right now it's solved for y squared, not y. So remember, the way that we undo a square is by taking the square root. So I'm going to take the square root of y squared, and I'm going to take the square root of x minus 4 over 5. Now notice here I didn't do plus or minus. Okay, normally when we're solving using square roots, we have to do plus or minus, but I didn't do that here because that domain is restricted and we only have that positive side of the parabola that we're looking at. So I don't need the plus or minus on this one, okay? So I'm left with y is equal to the square root of x minus 4 all over 5. Okay, and then I just want to write it back now in function notation by replacing this y with my inverse function notation, which is f inverse of x equals the square root of x minus 4 over 5. And I'm pretty sure on Newton it allows you to leave it like that. I don't think it makes you simplify the top or the bottom of the radical unless there's like a perfect square. Like say that was a 25, then we would just leave the radical on the top and simplify the bottom, okay? But I think it will let you leave it like this. I do want to show you one thing just in case it doesn't allow you to show it like this. In a lot of math classes, we don't like radicals to be left in the denominator, and so we do something called rationalizing the denominator, and that just means that we take our function and we write it with the square root on top and the square root on bottom. Okay. Now, if this is something that simplifies, like let's say the square root of 5 was something nice, like 3, okay, then we can just change that to 3. But here, since the square root of 5 is not a perfect square, not something pretty, what we do is we multiply this by a form of 1. So if I multiply this whole thing by 1, it's not going to change the value, right? And I can multiply by 1 by multiplying by any number over itself, because any number over itself equals 1. So what I'm going to do is I'm just going to choose purposefully to multiply by the square root of 5 over the square root of 5, because what that's going to do is create a perfect square on the bottom. Okay, so on top I can go ahead and distribute that, which gives me the square root of 5x minus 20 all over the square root of 25. And now the square root of 25 is something nice that I can go ahead and simplify so that I don't have a radical in the denominator. So this gives me f inverse of x is equal to the square root of 5x minus 20 all over 5. Okay, so in a lot of textbooks and a lot of math instructors will require that you go to this step. I don't think that Knewton has you go to that step. I think the ones that are multiple choice, you're able to enter like this. But if you work it out and you don't see your answer, or you don't see any choices that have square roots over the whole thing or square roots on the bottom, then you might have to go through this process of rationalizing the denominator. Okay, and you only have to do that when you end up with a square root on bottom that is not a perfect square. Okay, so if you have questions about that, please let me know. I'm happy to help explain that more if that was confusing. Okay, on an exam, on the final exam, anything like that, I would be okay with you leaving it either of these ways. I'm not super picky about that. All right, so let's look at another one. Undoing what's being done by the swap and solve method. So I want to take it out of function notation and write it with a y. So y is equal to 6 times the square root of x plus 8 minus 5. Again, notice here we have a domain restriction. That's because we have a square root, right? And whatever's under our square roots has to remain 0 or positive, right? We can't have negatives. So this is just making sure that we're aware that this function will have an inverse and that it is defined because of this domain restriction, all right? So now that I have it out of function notation, then I go ahead and swap. I swap all my x's with all my y's. So I have x is equal to 6 times the square root of y plus 8 minus 5. Okay. Now I just need to resolve it for y, and that will give me my inverse function. So I'm going to take my constant term and move it to the other side. And I do that by adding. So I have x plus 5 is now equal to 6 times the square root of y plus 8. And I'm solving for y. So remember, I need to get this square root by itself because that's what y is stuck underneath right now. So I'm going to go ahead and divide off my 6. So I divide off my 6. And that's going to give me x plus 5 over 6 is equal to the square root of y plus 8. Right? Now, just like up here, we used a square root to undo a square. If we have a square root, we can undo it by squaring, right? So I'm going to go ahead and come up here, and I'm going to take the square root of y plus 8 and square it. And if I square that side of my equation, I have to square the other side of my equation, okay? So now I have y plus 8 is equal to the quantity x plus 5 over 6 squared. And then the last thing I have to do is just move my 8 to the other side. So I go ahead and subtract 8. So I end up with y is equal to x plus 5 over 6 quantity squared minus 8. And then the last step I have is just to go ahead and put it back into function notation. So y is now my inverse function, which is equal to x plus 5 over 6 quantity squared minus 8. And we're just going to leave it like that. Okay. Maybe not the worst thing you've ever seen in your life. Maybe. All right. I want to do 2 more examples of another type of function. We've seen square roots. We've seen squares. But we are going to go ahead and find inverses of rational functions. So I'm going to introduce it here, and then we'll go over it some more in the next section as well. So let's look at these examples. So again, we're going to use the same process. First thing we do is take it out of function notation by replacing f of x with y. So I have y equals 6x minus 10 over 5x minus 5. And then we swap our variables. So everywhere we see an x, we're putting a y. Everywhere we see a y, we're putting an x. So I have x is equal to 6y minus 10 over 5y minus 5. So just replacing and swapping those variables, right? Now I need to solve this for y, and the way that it's written, I can't get these two y terms together when one's stuck in the denominator. So I'm going to go ahead and use what I know to get rid of denominators, which is clearing fractions. So I'm going to multiply on both sides by this denominator, because if I multiply it over here by 5y minus 5, then I can cancel those, right? But if I multiply this side by 5y minus 5, then I have to multiply this side by 5y minus 5. So these will cancel, and then I'm going to go ahead and distribute this x in. So I get 5xy minus 5x equals 6y minus 10. Okay? All right. So remember, our ultimate goal here is to solve for y so that we get our inverse function. So that means I need to get these two terms that have y's on the same side. So I'm going to go ahead and move my 6y over here to that side, okay? And then notice I don't need this term over here on the y side, right? Because it doesn't have a y. So I'm also going to move it over to the right-hand side in the same step. I'm going to add 5x to it, okay? And then I'm going to come up here because I ran out of room. So on this side, notice I cannot combine 5xy and 6y because one has an x and one doesn't. So I'm just going to write them out side by side. So I end up with 5xy minus 6y is equal to, on this side, again, these are also not like terms, so I can't combine them. So I'm just going to write 5x minus 10. Now, if you write that as negative 10 plus 5x, that's totally fine. I just like to write the positive one first. Okay, so now we have all of our y terms on the same side, which is great. Now we need to get y by itself. And the only way to get y by itself, if I can't combine these terms, is to factor that y out of the terms. So I'm going to go ahead and take out the y like I would a greatest common factor. So that's going to leave me with 5x minus 6. And now I can easily get y by itself because when it's written side by side with a quantity, that means that the operation is multiplication. So to undo this multiplication, all I have to do is divide. So I'm going to divide off my 5x minus 6. But if I do it on that side, I have to divide by 5x minus 6 on this side. Okay, so that leaves me with y is equal to 5x minus 10 over 5x minus 6. Okay, and I cannot reduce these because these are stuck like glue with these plus and minus signs. So the only time I could reduce is if I can take something out of both, right? So here, like I could take out a 5, but notice down here, I can't take a 5 out of both. So I wouldn't be able to reduce anyways. So I just leave it like it is. So then our last step is to put it back into function notation by replacing y with f of x. Or sorry, f inverse of x, right? So this is my inverse function, okay? So I know it sounds like a lot, so I'm going to do an extra example of this type, okay? Again, we're just going to replace our f of x with y, then swap all of our variables, and then get rid of our denominator by multiplying on both sides by that denominator. And then from there, it's just a matter of solving for y by moving all y terms to the same side, factoring out the y, and dividing off the leftovers. Okay, so let's look at another one, very similar. I'm going to take it out of function notation. So this gives me y is equal to negative 3x plus 5 over 7x plus 4. Then I swap all of my variables, okay, which is going to give me x is equal to negative 3y plus 5 over 7y plus 4. So just writing a y everywhere you see an x and an x everywhere you see a y. Now, this is what I want to solve for y. But I can't get these y's together when I have a denominator containing y. So I'm going to go ahead and just multiply both sides by that denominator. Okay, 7y plus 4. And the reason I'm doing that is so that these denominators will cancel over here on the right-hand side. Okay. On the left-hand side, I'm going to go ahead and distribute that x in. So I end up with 7xy plus 4x is equal to negative 3y plus 5 is all that's left on the right-hand side. Okay. And now I want to get my y terms together. So I'm going to move this negative 3y over here to this side. And then notice this 4x doesn't have a y. So I'm going to move it over to this side. So I'm going to do both of those in the same step. So I'm going to add 3y to get my y's on the same side. Okay, and I'm also going to move my 4x by subtracting. It doesn't have a y, so it doesn't need to be on the y side. Okay, now I can't combine these as they're written because one has an x and one doesn't. So I'm just going to write them side by side. 7xy plus 3y equals 5 minus 4x. Okay. Now I should be able to get y by itself because I have a y in both of these terms. And even though I can't add these terms together, I can use factoring, right, to pull out that y as a greatest common factor, which is going to leave me with 7x plus 3 equals 5 minus 4x. And now I can get this y all by itself by just dividing off that quantity that it's being multiplied by. 7x plus 3, 7x plus 3. Okay, so this tells me that y is equal to 5 minus 4x over 7x plus 3. And then the last step I have is, remember, I want to write it back in function notation. So I just replace that f of x with my inverse function. So f inverse of x equals 5 minus 4x all over 7x plus 3. I just leave it like that. Okay. All right. So on the next page, there are two for y'all to try. So I want y'all to take a moment, pause the video, work through number 1 and number 2. If you get stuck or whenever you're ready to check yourself, go ahead and play the video and we'll see how you did. All right. So here's the first one. We go ahead and write our function, replacing f of x with y. We swap our variables, so x goes in for y goes in for x. We move our constant term, then divide off our 4, and then to get rid of the square root, we just square it. So we square both sides, and then the last thing we have to do is to move that 2 over by adding. Okay, so our inverse function here should look like x minus 6 over 4 quantity squared plus 2. If you need to look at this a little bit longer, feel free to pause the video. I'm going to go ahead and move on and look at number 2. So looking at number 2, whoops, sorry, try not to have a glare here. I'll have to cover that up. Horrible glare. Okay, so on this one, whenever we start off, we replace our f of x with y and then swap our variables. And then just like the 2 examples that I got done doing, we have to clear fractions by multiplying both sides by 6y plus 3. So we can get that chunk out of the denominator, right? And then once we have it all multiplied out, it's just a matter of moving our y terms to the left, moving our terms that don't have y to the right, and then we can factor out the y and divide off the leftovers. So our inverse should be 2 minus 3x over 6x plus 5. Okay. So that is the end of this section. So you can now complete find inverse functions in your Knewton Alta homework. If you have any questions, please let me know. I'm happy to help.